Okay, from the last video, we now have the Excel tool pack installed, and we're going to replicate this table in Excel. So let's go to Excel. Let's go up here to Data Analysis, and we're going to look for the regression option. Click on that, click OK. Next thing is to input your Y range. Well, the Y is in fact your dependent variable. So you're going to select your Y. Now I'm going to put the titles in as well, what they call labels. And if I do that, I have to click this labels box to tell Excel that that first row is not data, it's a title. And then for the X range, I'm going to select the same thing, square feet. And again, title, and then select label. Next thing is I need to tell Excel where to put the data. So I'm going to go to the output range, put my cursor in the box, and I'm going to tell it to put the data. Let's have it put the data down here. Okay, just find a place for it. And then click OK. Okay. And what you will get is summary output. Okay. Now, let's compare these regression statistics with the data we already calculated. Well, the R squared, okay, we know that it's 0.5808, and that's actually what we got here. We just calculated it. Okay. Let's continue down. Let's go to the ANOVA. ANOVA stands for Analysis of Variance. And we have our sum of squared here, and we have regression, residual, and total. Let's see if the numbers match up. Well, our sum of squared regression is 18,934. Sum of squared regression, 18,936. Close enough, right? Rounding. Then we have our sum of squared residual or error, 13,665. Sum of squared error, 13,666. And then we have our sum of squared total, 32,600. Sum of squared total, 32,601. So this is a much more expeditious way to get to your results than going through the calculations. But now you know how to do both. We also have in our summary output the coefficients. Okay. We have the intercept, and the intercept here is 98.24. Well, if we go back up to our formula, 98.24, right? That was our intercept. And then we also have the coefficient on square feet, which is 0.1098. Okay, go back up here to our formula, 0.10977. Again, rounding. Okay, so we get the same numbers. Okay, let's move on now to some of the other elements of the Excel output. Statistically significant coefficients. If you recall, in the last session on hypothesis testing, we were trying to assess whether our sample data, whether it was the mean or the proportion, could be used to infer about the larger population. And we're going to do the same thing with our coefficients. So we need to create a hypothesis test to determine if our coefficients are significant. And what that means is our intercept and our square feet. These are the coefficients that are telling us how our X value is correlated with our Y value. More specifically, how square footage is correlated with home prices. And so these are important pieces of information. But remember, we're collecting a sample. Maybe we selected 10 homes from a population of 1,000 homes. And we're using that random sample to infer about the larger population. And when doing that, you have to determine if your sample results coefficients are statistically significant. And that's where the hypothesis test comes into play. Okay? Our null hypothesis is that the true population beta, which is the coefficient, is equal to 0. And the alternative hypothesis is that the true population beta is not equal to 0. Which of these would a researcher want? Well, if you go out and you collect a sample on home prices in square feet, and you run this regression and you get these coefficients, okay, you want these coefficients to tell you that the true population coefficient is not equal to 0, thus demonstrating based on your sample that there is a relationship between square footage and home prices. If you take a sample and get coefficients that cause you to not reject the null hypothesis, then your sample coefficients are supporting the idea that there's no relationship between square footage and home prices. Researchers don't like to collect data and find out that they have no relationship to explain. All right, so how do we determine if we reject the null and accept the alternative, or do not reject the null? And the answer is we have 3 routes. The first is the t-stat. Well, you remember the t-stat. The t-stat tells us how many standard errors our sample data lies from the hypothesized population mean. In this case, it would tell us how far our sample coefficient lies from the hypothesized coefficient of 0. In fact, if you take this number here, 0.10977, and you divide it by the standard error, 0.03297, you will get 3.32938, which is the t-stat. So again, the t-stat is just telling you how far in terms of standard errors this value, our sample coefficient, lies from this value, our hypothesized population coefficient. And in order to determine if we should reject the null and accept the alternative, we need to compare this computed t-stat to the critical t-stat from our table. So let's do that now. Here is our t-table, and what we need first is the degrees of freedom. Well, in our sample of homes, we had 10, so we need to subtract 1 and get 9. That puts us here. And we're going to do a 95% confidence interval for this data set, which is a very common one. And that means we need 2.5% in each tail. So the tail probability here would be 0.025. So we have 2.228. And you can also see this from the table because down here it shows a 95% confidence level. Okay, so our 9 degrees of freedom is, I'm sorry, it's actually 2.262. 2.262. Let's now go to our t-stat here. And because we have a computed t-stat of 3.2, and that is greater than the critical t-stat that we just got from the table of 2.262, we would reject the null and accept the alternative. This value here lies too many standard errors away from 0 to support that the true population coefficient is 0. Ordinarily, we're not dealing with such small samples. We're dealing with larger samples. And that means often we can use a t-stat of 1.96 as our critical value as long as we have a sample greater than 30. If we don't have a sample greater than 30, then we need to do what we just did, which is find the critical t based on the table. Okay, the next way of assessing whether you have a statistically significant coefficient, right, is the p-value. The p-value is revealed in our data here. And what this means is it tells us the probability of getting a sample of this value if the true population coefficient were 0. So clearly, if you have a really low number here, like here we have 1%, there is a low probability of getting a sample with this coefficient, which we did, if the true population coefficient were 0. Now, the standard is going to be if the p-value is less than 5%, then you would say we have a statistically significant coefficient. And here we have a p-value of 1%, meaning we have a statistically significant coefficient. Another way of putting it is if the p-value is less than 5%, then we can reject the null and accept the alternative. If you do this correctly, the t-stat that establishes whether you have a statistically significant coefficient will not contradict the p-value establishing that you have a statistically significant coefficient. They will simply mirror each other in terms of information. Now, why did we use a p-value of less than 5% as our standard for establishing the statistical significance? Because we already said we're going to use a 95% confidence level. And that means that there is 5% of our data in the tails, which means 5% of the time you would expect to get sample coefficients that lie in the tail. But 95% of the time, you would not get sample coefficients that lie in the tail. And since we have 1% here, we're clearly getting a coefficient that lies in the tail. And that's very unlikely if the true population coefficient were 0. Okay, the third way of determining whether you have a statistically significant coefficient is the confidence interval. And we built these in the techniques of estimation section. But here it's telling you the lower confidence level and the upper confidence level, assuming a 95% confidence interval. Okay. So the lower confidence level is 0.03374. The upper confidence level is 0.1858. What does this mean? It means that based on our sample, we believe with 95% confidence that the true population coefficient is between these values, that this is the lower bound and this is the upper bound. Okay? And that, as long as there's no 0 in there, implies statistical significance. If, based on our sample, we believe that the true population coefficient on square feet is 0.03 to 0.18, then we believe that it is not 0, because there is no 0 in between here. And therefore, we must reject the null and accept the alternative that beta is not equal to 0. Again, this data here is not going to contradict this data or this data. It's like 3 little windows to looking at the same thing, statistical significance. 3 little windows to establishing whether you should reject or not reject your null hypothesis. Okay? And in this case, the t-stat tells us reject the null, accept the alternative. True population coefficient is not 0. The p-value tells us reject the null, accept the alternative. The true population value is not equal to 0. And this tells us, the confidence interval, that the true population beta is not equal to 0. Okay, 3 routes to the same end. This is important because if you do get a contradiction in these numbers, something went awry. All right, the conclusions. Well, the square footage of homes does influence the price of homes. We collected a sample and we have statistical significance on our square feet. So that tells us that based on the sample, we now know something about the population. We'll pick up with the rest of this in the next video. Thanks.